and start the recording so I don't forget. Hi folks, happy garbage day. I was proud of myself for backing out of my driveway this morning in the very narrow entry between snow piles and not hitting the garbage can. I win. We gotta celebrate the little victories in life, don't we? I did not win last Thursday when I accidentally shut down the recorder halfway through class. Remember when the thing popped up to restart? I think I X'd out of the wrong box. And I discovered that after the fact, so if you haven't seen it, I recorded a separate video on Friday covering what that second half of the video was. So it's the same content, just a lot shorter because I'm not talking to anybody. So. But anytime that happens, I promise I will make a video so that we have a relatively complete record of everything that was covered in class in case you can't be here or you just want to hear it again. Sound good? Fair? All right. So I've been busy putting up some new stuff for you to do. So I looked through homework 0. Everybody turned it in. Everybody did the final submit button and did it for real. Good job. That rarely happens. Usually there's one person who forgets to submit and then enter the ID, but it looks like everyone got it. So your 2 points of extra credit, up to 2 points I should say, are online. You can check the totals in the homework portal. Since then, I've made available your first formative assessment. That is an icon. So you log in under quizzes. I think it also shows up under assignments. Those are going to be off the top of your head types of questions usually, sometimes definitions, sometimes story problems. The last question merits a little bit of explanation, as has become my tradition for the first formative assessment in all my classes. I want you to tell me what your theme song is. Like your walk-up music, right? Like if you're coming into the game or the match or the tournament, whatever it is, and like there's music playing overhead and people are cheering for you, what song is that? That's what I want to know. Any language, I'm okay with profanity. I'm not easily offended. So whatever motivates you. And if you're willing, if you could paste in a link to the YouTube, I will build a playlist for our class so that we can all hear each other's theme songs. It's my way of discovering new music because most of what I listen to is very, very old. Deal? All right, I'm still thinking about what mine is going to be. I try to change it up every semester. So I've narrowed it down to a few. We'll just got to see what the feel is that day. And also, I've put up homework 1, so that is available right here. It will also be submitted via icon as an assignment. There's a spot for it already. And I thought I would show it to you real quick so you can see how short it is. So the instructions, and then a couple of questions that you're answering, okay? That's it. The idea here is for you to do some background examination of the items or the scales that you're going to be examining in homework 3 and homework 5. So what psychometric evidence is there for the dimensionality, the reliability, the validity, and that kind of stuff for the items you're going to be working with? If you're working with brand new items that like literally you just invented and they've been administered for the first time and you don't have a lot of this information, that's okay. Just tell me what you can. If you're reading the article and it uses words that you don't know what they mean yet, that's okay too. I hope that by the end of the semester you will know, so you can ask questions in here as well. So I just want you literally to type your answers in here in the Word document and send it back. I will insert comments or questions, and if needed, you can revise this and turn it back in for any missed points, but usually that's not necessary. So you don't have to have the data you're going to analyze yet, but you need to sort of land on a project or a scale type so that you can do this assignment. So that is due in 2 weeks, and the first formative assessment is due next week. All right, questions on that? Not yet, I imagine, right? Not yet. Okay, so then we were looking at an example last time. We were talking about stuff. So let's go back to this, shall we? As a little way of reviewing, wading back into the week. So we were talking about, this example is from my real life. As a graduate student, I helped with the development of the Family Professional Partnership Scale. I remembered the name. That has 2 subscales pertaining to how a service provider addresses and takes care of the needs of a child with disabilities, as well as how well the service provider works with the family of the child with disabilities. And this is an ordinal response format of 1 to 5. I'm going to pretend it's continuous, as I did in this article, and that was because I didn't know any better. So you'll know better after we get through this experience. So we went through the first subscale last time. We started with 11 items. looked at some classical test theory type statistics. So item difficulty as indexed by the mean of the items, and difficulty is actually backwards because in this metric, higher scores mean that items are less difficult or easy, or that they're easier to agree with in this case. Highly skewed data as indicated by a median of 5 on a 5-point scale. Pearson correlations among the items. This is something that I would always encourage you to look at because if there's any big problems, they will jump out at you. So do you remember what I said what it would mean if it were game over? What would this matrix look like if it meant game over, there's no point in continuing, you don't have a factor here? What kind of pattern would indicate that? And Zoomers, I'm watching the chat. You can play along too.
Low correlations?
Low or no. Yeah. If your items aren't related to each other, they can't possibly be measuring the same thing. Game over. So low correlations are not good. However, these are Pearson correlations. So I'd want to keep in mind that for binary and ordinal items, this isn't the best measure of association. It's going to be bounded, especially for binary items. The fact that I have heterogeneity in correlation makes me think that either there might be multiple dimensions in here or some items measure the trait better than others. But beyond that, my eyeballs are not strong enough to be able to ascertain that. But if you expect to have subscales, right? If you think that your items are measuring more than one trait, I would encourage you to group together the items that go with each chunk and see if they form little pockets of correlation in here, because that's what you should see if you're right. Then we looked at a couple of classical test theory, the other ones besides difficulty. What is the other one? Property. Also starts with a D. New vocabulary from last week. Discrimination. Yes, that is a word that will stay with us this semester. The only difference across models is how it is indicated. At this point, we're not fitting a model. We're making assumptions instead. And discrimination is indexed by the item rest or item remainder correlation. So this is the Pearson correlation between your item response and the total of all the items in the analysis minus that one. So we want these to be big or little. Make it multiple choice questions. Big. If I want a nice, happy, discriminating item, big. And this column, does this column give you alpha? No, not most of it. This one's alpha. What does this column tell me? Yes, if the item were removed, this is what your alpha would become. I learned this as alpha if deleted. I guess that was too big of a label, but actually it's not. They could have fit it. So, Stata programmers, fix this, please. So all of these are lower than the alpha, which means that alpha would not be improved by dumping any of them. So there's no items that stand out in terms of their statistics. But I flagged these two based on their content, because these two in bold have nothing to do with the child per se and have to do more with the family relationship. So we decided to move those to the other scale and then look at how well they fit with that one. So we did the same thing in R. Less helpful labels continuing, but there is an R dot drop that tells you the alpha. So let me ask you this. Alpha of 0.91, is that good? What's the highest alpha can be? 1. What's the lowest it can be? 0. Negative 1. It can go negative. Alpha is a function of two things. Average inter-item correlation, which is how it can go negative, and one other thing. What is it? Number of items. The more items you have, the higher your alpha. So 0.91 is not terribly impressive for an 11-item scale, I would say. Do you remember we had some charts about this? Should we talk about those a little bit? Since I'm asking formative assessment questions about it, I figure that's only fair. Where's my charts? Here's my charts. Here we go. So 11 indicators and an alpha 0.91, that means average inter-item correlation somewhere around 0.5 for this particular scale. Not terrible, but 0.91 sounds more impressive than I think it actually is. And here is how you can work backwards to figure out what your inter-item average correlation must have been. And here's an egregious example of how it can be low and still have really good alpha. There are three things, though, that we have to assume in order for alpha to be an accurate measure of reliability. What's the biggest one? Starts with a U. That's it, unidimensionality. It's the idea that the items all measure the same latent trait. That's the biggest one, because if that's not true, alpha does not make any sense. So if you see alpha as a measure of reliability for subscales and then they give an alpha for a total score in a manuscript, disregard it. It does not mean anything. Plus, it's probably inflated because you have a whole bunch of items in there. Then sort of moving down in terms of importance, what else does alpha assume about how the items relate to the trait? Let's see if we can get everybody to talk at least once today. And feel free to read from the slides that are nearby this one, but I'm not going to put it up just so we can have some suspense.
They have the same true score?
They have the same true score, I would say, is the same thing as unidimensionality. But related to that, how do they relate to the true score? You don't remember? Want to phone a friend? I think Kendall wants to be your friend.
Oh, they all relate equally?
They all relate equally, yeah. Equal discrimination. In practice, it translates into equal item covariances across the whole matrix. So the example here is a correlation matrix on the previous page. It would be parallel items if it were equal correlations, which adds on the requirement of equal error variances. That's Spearman-Brown reliability. Alpha reliability is only equal covariances. And one more thing. What about the errors of the items and how they relate to the trait? Uncorrelated. That is a special vocabulary term you will learn this semester in this class and in the IRT class called local independence. The E's are unrelated. In English, what that means is that the only reason that these items were correlated in the first place is because of the common trait they measure, and after you condition or control for that, what's left, the errors, the residuals, are unrelated. In practice, that's an empirical question. And I would be highly surprised if at least half of you didn't end up adding error correlations to your models when we get to CFA. Because what can happen is that items that have something else in common will be more correlated than what is predicted by the model. Like if you have two items that are reverse coded and the rest are not, those two are probably going to need a residual correlation. If you have content that's overly specific, so for instance, if you're measuring something like social anxiety and you have two different items related to public speaking as a particular way that that could manifest, those two might correlate because of that one extra common thing of being afraid to talk in public. Clearly, I don't have that problem. But I have other forms of social anxiety too, instead. Maybe it's not unidimensional after all. I don't know, that's not my research area. I'm not a psychologist today, I'm a methodologist. Okay, so all of these things that have to go before alpha, we're not dealing with yet. But that's the next unit that I hope to start today. Okay, any thoughts or questions on that? All right, then let's look at the family subscale. Shall we? Why not? So for this one, I'm starting on example 3, page 4. This is the other subscale within the same measure, and because I showed how to do this in Stata and R the first time, I'm going to show how to do it in SPSS and SAS this time. You can pick your program, I don't really care. So in SPSS, they have a routine called reliability. The last I checked, it uses listwise deletion for missing data though. So SPSS will give different results than the other packages as a function of missing data. In SAS, I'm using proccore, stands for correlation, with the alpha sub-option. And this, by the way, this out command is how I got a correlation matrix saved that I then pasted into Excel and made the pretty colors. I'm sure there's more direct ways to do that, but sometimes the easiest way is just what I'm going to go with. So I exported the matrix and then added the formatting, and both of those files are in your download folder. So let's look at the descriptive statistics for the family scale. The content of the items is out here. So means, on the high side again. Looks like everybody strongly agrees with everything. Pearson correlations. It kind of looks like a cross to me. Like item 20 here has more red relatively than the others. Eyeball test at least. But I do have correlations, so it's not game over. Alpha for these items, so I believe at this point we have 12, excuse me. We had 9 before, and then we had 10 before, and then we added the 2 from the other one. Alpha of 0.92, so around the same as what we had before. Then we get into item diagnostics. So SAS gives you, this is SAS output by the way, the raw versions, and it also gives you standardized. Just ignore those for the time being. Correlation with total, what does that tell me? Starts with a D.
Discrimination.
That's my discrimination. So if I'm looking down this list here, I flagged 2 that looked markedly lower than the rest. How about this column? What is that? Can't be alpha.
Alpha if deleted.
Alpha if deleted, yeah. And so original alpha is 0.919, so 0.2. This one especially would make alpha higher if it were removed. This one is heading in that direction. So I flagged those 2 for those reasons. So when we were actually in meetings looking at these results, this item, I was like, you need to get rid of it. It's bad. And the other scientist on the project who had the content expertise in this area said absolutely not. Protecting your family's privacy is something that they felt very strongly needed to be in here. And if you look at the content of these items, do you see any other items that would get at that same idea of protecting privacy? Being available, being honest, using words you understand, planning meetings at convenient times, returning messages, keeping appointments, showing respect, listening without judging, being dependable, paying attention, and being friendly.
The only maybe is showing respect for family values and beliefs, but otherwise it's pretty much its own thing.
Yeah, it's pretty much its own thing. So there's 2 ways to look at it. Is that based on the numbers here, this doesn't look like it fits with the others, and we can get rid of it. That's a reliability argument. They were making a validity argument, that the construct they're trying to assess has this as part of it. And because this is not mentioned in any other items, we need to make sure that we keep it, even though it's not as related, so that we have the broadness of the construct we want. So there's not necessarily an easy answer here. It really is both like art and statistics at the same time. So as you're looking at your results, I'd strongly encourage you to have open simultaneously with whatever model output, literally the items, so that you can see what might be underlying the patterns and decide on the basis of both reliability and validity what items you'd want, what you want to do with your items. Whether you would want to make a separate subscale, drop them, add error correlations, or things like that. So they're like, nope, we keep that. Okay, and this one, also they wanted to keep because there was nothing else about honesty in here. But I suspect that the reason this might be a little lower is the caveat, even when they have bad news. So honesty is a good thing, right? What if your mom gives you a necklace for Christmas that you really don't like? You gonna be honest? You're gonna smile and say, thanks, Mom, I love it. That is different than not being honest about things that you really need the honest answer for. So that's my hypothesis. I have no way of examining that hypothesis, but that's my hypothesis. So when you add caveats or exemplars, sometimes you do more harm than good. So we did something completely different. We didn't want to have this many items. We wanted it to end up with 9 to match the other scale. So what we decided to do is remove the items that we felt were overly specific. planning meetings, returning messages, keeping appointments. That's available when you need them. So we decided just to stick with that. So 17, 18, and 19, I think, was it? Planning meetings, yeah, these three. If you were developing a measure in which you were first sort of screening for big problems, like someone said, the person I work with is not available, then these questions might come in handy as like a second step. Okay, where is the disconnect? Do they not answer their phone? Are they literally not there? Do they not return messages? And so forth. So we thought that these three things were adequately covered by this and decided to remove them, even though their stats were okay. So then we ended up with this as our composite. Privacy is still on the low side, but they wanted to keep it. Honesty is still on the low side relative to this. Alpha ended up being 0.88 instead of 9.2, and we decided we would live with that. And that's the end of the first part of it. Then we did a confirmatory factor analysis and looked at the factor structure as being 2 dimensions, and it actually held. So we said, yay, us, and wrote it up and turned it in. And it's been cited 300 times. Measurement papers tend to get cited because anyone who's using your measure, no matter what they're looking at, has to cite you to do it. So these sorts of projects that I worked on in graduate school are actually some of my highest cited stuff because people have continued to use the measures that I helped in developing. So, yay. All right. So thoughts or questions on that? No? All right. Bye-bye example. Back to lecture 3? Why not? So we ended with past alpha, past this, some true-false questions. Is KR20 the same thing as alpha or no?
Under certain conditions, yes.
When is it different?
Can't KR20 be used for multidimensional?
I think if it could, it would have to be per dimension still.
Okay.
But it actually came first. Alpha was a generalization of this. But anything that's based on means, variances, and covariances is going to be equivalent to alpha. So we have KR20 as a binary version of alpha, but the problem is that for binary data, Pearson correlation is not a good measure of association. It's lower bounded for variables that have divergent means, that have skewness to them. So we looked at, and I got out paint to draw some other kinds of correlation. So I'm not going to draw on paint again, but that'll come back later in the semester. I'm just planting seeds that there are better ways to do it, and I'll show how you can do those. So then picking up on slide 25, we'll start there. So I've answered a couple questions about folks on this topic, so if you are one of those folks, this is for you. So the concept of reliability when it comes to verifying across raters is also another situation in which I would not recommend Pearson correlation most of the time. The problem is that Pearson correlation standardizes each rater's outcomes separately. It has a separate mean and a separate variance, but differences in mean and variance are something that you might want to know about when you're looking across raters. Is one person systematically pickier, so they're rating everybody lower? Is one person a lot wider in terms of how they're using the scale relative to sticking in the middle? These are things that you would want to know. So to do that, you can compute a different type of correlation, which is known as intra-class correlation. And if you're thinking, hey, Lisa, is that the same vocabulary that we learned in all the other multi-level modeling classes? Yes, it is. It's the same. There's a whole bunch of different variants of this, but basically the idea is that intra-class correlation refers to some kind of ratio of variance components, where what's in the numerator relative to some kind of denominator of total, and you can put different terms in there based on what type of agreement that you want to have. So this one would be an example of absolute agreement, where if you have two raters, you would use a common mean and a common variance across them, and then compute the rest of the story here. So we can think of this as, at the end of the process, a ratio of the variance between targets That's the part we should have, right? Because the people you're rating should be the only source of variability if your raters are agreeing. Relative to that, plus some kind of error term, and then the variability across raters. So really, it's this latter middle part that makes this different. And you can readily extend intra-class correlation to more than 2 raters. And if you estimate these models using maximum likelihood, you don't have to have a complete crossing. You don't have to have everybody rate every topic. You can have planned missing data in here. And if you're thinking, hey, Lisa, doesn't that sound like G-theory? Yes, it does. It's the same thing as that too. Not to be confused with Spearman G general intelligence or any other G. G-theory in this program refers to generalizability theory, which is an extension of trying to figure out what we used to just call error as one pile, how much of it is due to various specific dimensions of sampling. So here's a picture to illustrate when you might come to a different conclusion. Let's say that I have rater 1 and rater 2, and in the first scenario here, they're very comparable. So similar means the same standard deviation. In that case, Pearson correlation and intra-class correlation are going to converge to nearly the same answer, versus something like this, where rater 2 is systematically higher, then the intra-class correlation is a lot lower. So what I see folks do in practice is 2 things. They might compute a Pearson correlation between the 2, which ignores mean differences, and then also compute a t-test to examine mean differences. Intra-class correlation does both of these things at the same time. And so then the question is, do you want absolute agreement or only relative agreement? This is absolute agreement. Relative agreement would factor out differences in means and other things like that. So there's a whole literature on this. Intra-class correlation is the key, though. Start there as an idea. Other things that people use reliability for, I don't know if you've seen this in some of your other coursework, the Spearman-Brown prophecy. I saw this as an undergrad. No, you haven't? It's okay. Just pretend you never heard it, because it assumes parallel items. So this is a formula that allows you to extrapolate what your reliability would have been had you had more items. And because there's nothing in the formula that says what kind of items, how good they are, how correlated they are, that means it's parallel. So all the items that you already have are equally related to the latent trait and have equal amounts of error variance, and all the items you'd add, that would be true for as well. So, too much. This is a testable assumption once you have the data, and I've actually never seen it hold in practice. So, try to put this all together in terms of model assumptions and how they translate into different types of reliability. In the next unit, I will show you how to actually do this. But if you use alpha, that implies tau equivalent indicators is what people say, true score equivalent or equal discrimination. I hate the phrase tau equivalent because tau is not going to be what this parameter is in the model. Tau is going to be for intercepts, or that's in a lot of people's notation instead. I use mu so that we can avoid tau altogether. It translates into equal covariances across the items, whereas using Spearman-Brown reliability translates into parallel. So it adds the constraint of equal discrimination plus equal error variances, which translates into equal correlations instead. And there is a very interesting article, I think, on your reading list. So this one, I thought they did a really nice job of describing this, demonstrating it mathematically, and actually showing in SEM software how you can prove that you can rearrange a parallel items CFA model into having the trait have the same mean and variance as, and a perfect correlation as the sum score. So when you add things up, you are assuming parallel items. And I mention this because this article pissed off 2 other people so bad that not only did they write a rejoinder, but in our professional society meeting, they used their time at lunch to badmouth these people. And the time at lunch was supposed to be us talking about like updates on our lives and our careers, like babies and promotions and that kind of thing. No, they spent the time saying how terrible and wrong this was. Okay? So they wrote this rejoinder, which basically was, nuh-uh. And so he wrote back, yeah-huh. And then the editor was like, no more, you guys are done. Go to your corners, go to your rooms. And so they were like, yeah-huh, in a different journal. So there's like 4 papers strung together about this. And ultimately, I think the first one was right. Because if you read the rejoinder, they came with receipts, as we say nowadays, right? They had the math, they had the simulations, they had the algebra, they had all the things. So this, I think, is encountering some pushback, but you can't argue with math. Like, this is what it is. So be aware that adding things up and then calling the sum total a trait is the same thing as assuming parallel items. You can prove it mathematically. Another thing that bugs me is when people pretend like they have higher reliability than they should. So you can estimate correlations between two variables that have been disattenuated for their unreliability. So for instance, if I have two measures that have low reliability, 0.25 for one, 0.55 for the other, and the correlation between them is 0.38, I can throw that into this formula and say, now my disattenuated correlation is 1.03. You're like, wait, does correlation go up to 1.03? It does not. So yeah, there's not quite something right here. However, this is fundamentally the basic idea of structural equation modeling. It's the idea that once we take away all the error from our items and we save just the good stuff, the relationships of that trait with other traits that only have just the good stuff should be stronger. That's the logic. But at this point, I would not believe whatever people are saying this variable is. If you have reliability that low, it's hard for me to think that that's a consistent measure of anything. So like game over from a theoretical perspective at that point. All right. Okay. How are we doing? Question.
Is attenuation corrected the same as disattenuated?
Yeah, I'm saying what people usually say is the correlations have been disattenuated for measurement error versus you can say this is an attenuation corrected correlation. Yeah, those are synonyms to me. And I think they're sus. That's my take-home message. Other thoughts? Zoomers are awfully quiet today. Can you still hear me? Attention check.
Yes, I can hear you.
Yeah. Thank you. This is like the CAPTCHA thing. You know, how many motorcycles do you see? You still, if you're reading this question, enter 5. Those kinds of things. All right, so reliability is often thought of as like this goalpost that you have to meet for your study to be publishable, right? You have to have good enough reliability and then you can go on. But if you're actually using the scores to make decisions about people's lives, then I think it's much more important to think about what the reliability implies for the standard error of measurement. So for now, I'm working with the classic formula in which everybody would have the same standard error of measurement. That will be an assumption that we make in CFA as well. Eventually, towards the end of the semester, when we talk about IRT models, the standard error will be a function of where you are on the trait and the amount of information at that point. But you can use this little formula here to build a confidence interval around a total score for what it is likely to be, 95% of the time in this case. So this is, I think, potentially a more useful way to think about reliability when it comes to making decisions. So let's say that I have variance of a total score of 100, and I'm interested in making an interval specifically for somebody who got a 50. So if I have a reliability coefficient for this total score, using alpha, let's say, 0.91, variance of error of 9, and then standard error of 3, that translates into this interval right here. If I have a reliability of 0.75, which some folks would still say, it's not bad, that translates into an error variance of 0.25, standard error of 5, and a much wider interval. So then what if you had something like you needed to have a 45 or higher to be something, right? To pass this class, to be able to go on. Like someone with a 50 looks on paper, like, yeah, they're higher than 45, but are they? Like if this is their interval, can you be certain that they're higher than 45? Not really. So to me, it's interesting that people take like the test score and use that to decide whether or not you meet some cutoff, such as the English test requirements for our university and other types of things like that, without considering the error around it. Unfortunately, most standardized tests don't give you a standard error. They just give you your score. So it's impossible to tell. Had a question from the Zoomers. Why do you think they are sus, the attenuated correlations? Because they're not real. I think that to the extent that most of the variability in a measure is not consistent, is not the trait, that removing all of that information and focusing on the tiny bit that's left is, to me, just seems like too much of a jump. That's an opinion. So that's why I use the words like sus as opposed to wrong. I'm expressing my opinion. So I want to show you an example that you can no longer make because the data that I used to build this example has been taken down from their website. These are confidence intervals around GRE scores. This is from the 2021 booklet. They used to have this publication called the GRE Guide to Interpreting Test Scores, and it is no longer available, or I could not find it at least. Using results that they published in this manual for the verbal GRE score, mean of 150, standard deviation of 8.5, here's the range of the possible scores. This is what they report for conditional standard errors of measurement, meaning differing as a function of where you are on your score. So range is 130 to 170, that's why I put the dotted lines here. Does anyone see anything, I don't know, maybe weird, sus, implausible about these intervals? What's the lowest score you can have again?
130.
That one. Their own data is suggesting impossible bounds of their confidence interval. And by the way, where these standard errors came from is a simulation using a 3PL assuming perfect everything. Yeah, the data are in the thing. I have it if anyone wants to see it, since you can't download it anymore. Same thing on the upper end. No, you can't have an upper end of 173. It doesn't work. But what is interesting to me is that if you look at the points along this where maybe admission decisions would be made, right? If you have a score this high, you have a good verbal score. If you have a score this low, you don't have a good verbal score. Note that I'm saying score and not ability, right? Because score is what we're going with here. This is the gray area where maybe you get admitted to your program of choice and maybe you don't as a function of who cares about these scores. The difference across applicants of 145 to 155 could be most of the variability in that sort of medium group. So a score of 150 means quite a big range. In the old GRE, on a scale of 300 to 800, the standard error of measurement at a score of 500 in the middle was 50. So if you got a score of 500, that was really somewhere between 400 and 600, which was all of the practical variability that you would see in an applicant pool. So I first learned this when I was building a presentation for Psychi. I was the undergraduate advisor when I was at Nebraska for their Psychology Honor Society Club thingy. And they wanted me to talk about what it meant when they changed the scale from 300 to 800 into this new one that they have here. And so I went digging in all of this documentation. And it turned out that, yeah, like they have fewer possible scores in the new scale, but like the issues of wideness of the range from what their model implied standard errors would say are still there. So until the GRE starts printing standard errors next to the scores, I'm not paying attention to it. Do you know what I pay attention to when I look at admissions? First thing I go to, their letter. Number one, is it grammatically correct? Number two, does it say something like, I'm excited to go to the University of Colorado because, attention to detail. And number three, do they know what they want? Why here? Why now? What do you want to get out of grad school? If they can write decently well, they have attention to detail, and they know what they want, to me that's like 80% of the variance in terms of like what makes a good grad student. Then I go to the letters, then I go to the transcript, maybe I stop by the test scores. That's my take. I had a professor in my graduate program that would not take people with perfect GRE scores. She flat out wouldn't take them. And she said it's because that is probably someone who is never able to leave well enough alone and is a perfectionist. If you got a perfect score on the first try, then that is an unfair characterization, but there's not a lot of people who can do that. So for her, it was a red flag of somebody who was not going to be able to get stuff done and turned in, even if it was not perfect. So this is verbal. How about math? Or quantitative, excuse me. Same thing. Still the same issues of out of boundsness and very wide ranges in the middle where most of the decisions would be made. So this is what I want folks to think about in terms of how reliability translates into practice. How wide is the range around someone's score, and are you comfortable with how wide that is? If you're not, you need better reliability. And that probably depends on what you're trying to do with your measure. So, thoughts or questions? Comments?
Would we not also be worried about the fact that the variability is decreasing as we move across the spectrum?
That's what, so that to me is also sus, because it implies that they have more information at the highest levels, which unless, it depends on the item pool and how they do it, but it seems unlikely that they would have more items at the high side than targeting the middle side. So in this case, I would argue you want maximum sensitivity in the middle, around the folks where you're like, is that good enough or not? Not amongst the people who clearly have mastered whatever this is supposed to be measuring, and not amongst the people who have some work to do. And they don't have any information on the writing test, so I couldn't do that one. But. All right, so wrapping it up. In classical test theory, the idea is that the total score is our best estimate of the latent trait. We're assuming unidimensionality in doing that, which is testable. You will hear me call this an ASU measurement model throughout the semester. That stands for add stuff up. And sometimes it's add shit up, depending on the day, how I'm feeling. So we are going to explicitly test dimensionality. We are going to explicitly test whether items are equally discriminating, whether there are additional relationships in your items beyond the ones that you're thinking about, correlated errors and whatnot. But in terms of how you would improve your measure, because we are assuming all items are the same, that logically says what kind of items do you need to make your test more reliable? More. Just need more. That will change throughout the semester. And if we are using one coefficient to characterize reliability, that translates into one standard error of measurement, meaning that everyone is measured equally well. That is highly unlikely unless you have as many items at each point on the trait. Usually they're focused in the middle. So, unlikely. Ta-da! Okay. Thoughts or questions about that? Okay, it's 1:15, then I was right. That means we have time to start CFA today. I rhymed. You're like, why are you so excited? I do this for a living. I picked this. You know, it's funny, whenever I go and have to get blood drawn, I am the biggest baby about it ever. Like, I'm one of those people that's like, I can't look. And I used